So hey guys, welcome to another video on microprocessors. And in the previous video we have already discussed about what are microprocessors, and we have also discussed about some of the basics of memory. We have discussed about segment addresses, some offset addresses, and I will just suggest you to watch that video, the previous one, in this playlist, in the microprocessor playlist, and then you can come here and you can watch this video. So in this video, what we're going to do is we're going to particularly understand the architecture of the 8086 or 8086 microprocessor. So the architecture, in architecture, we just study the different components of the microprocessor and we understand how a microprocessor is actually working. And we will study this whole architecture. You can see in the blue color is the architecture of the 8086 microprocessor, and we'll study this whole architecture unit by unit, and we are also going to study all the components. And here you can see I've drawn the memory, which is the main memory, the RAM, and some segment addresses. So we're going to discuss all of them in this video. So before we start, before we just start with the studying with the architecture, I will just recommend you to like this video and subscribe our channel so that you can get updates about some more videos that I'm going to upload related to microprocessors or some other videos. And please make sure to share this video with all of your friends who want to understand microprocessors. Alright, so let's start with the architecture of the 8086 microprocessor. So in this whole diagram, in this whole architecture, you can see that I've divided this architectures into two different units. So you can see this line, it is dividing this whole architecture in two different units. So the first unit is the BIU, or the bus interface unit. The second unit is the EU, short form, and it stands for the execution unit. So the main reason why we have divided this whole microprocessor into two different units is because of a concept known as pipelining or parallel processing. So a parallel processing is basically when the microprocessor is executing, or it is executing instructions in the execution unit. At the same time, the bus interface unit can fetch the instructions. So we will study this pipelining or the parallel processing once we will be able to understand how these two units are actually working. So let's start with the first unit, which is the bus interface unit. So the bus interface unit does three things, and these three things are: the first one is it fetches the next instruction, it calculates the addresses, and it manages the queue. So now first thing is fetch next instruction. Now first of all, I would just like to say that you can see these symbols in this architecture in these two places. So you can see in both of these units there is this symbol. This symbol is basically stands for an arithmetic circuit, and arithmetic circuit is used to perform some calculations. It can be some calculation related to some instructions, or it can be some calculations related to calculate the addresses, which is the second step. Alright, so let's study about the BIU now. So BIU, the bus interface unit, fetches the next instruction, and we know that all the instructions resides in our main memory. So this is the main memory, and you can see that we have divided this main memory into four segments: 1, 2, 3, and 4. And these segments are the CS, SS, DS, and ES, the code segment, the stack segment, the data segment, and the extra segment. And these are basically the conventional names used for these segments. Now one important thing to note here is that these segment has some starting point, which is the code segment address. We call it as a segment address, and if we see a particular segment, there are various instructions in it. So every instruction can be accessed using the offset address, and we have already studied this concept in the previous video. So now what is done, you can see in this part, in this section, in this one, you can see that this is a box which contains the CS, the SS, the DS, ES and IP. So let's discuss about this. So 8086 microprocessor, a very important thing to note here is that it is a 16-bit microprocessor. It is a 16-bit microprocessor. That means that the instructions that this processor is going to deal with are of 16 bits. And so you can see in this structure we have CS, SS, DS, ES, and here I have written that these all are of 16 bits. So the segment addresses inside the code segment, the stack segment, the data segment and the extra segment are of 16 bits. Alright, so one important thing to note here is that these are not the segments, these are not the memory segments, these are known as the segment registers. This means that if you consider this main memory, the microprocessor does not directly access the main memory. Whenever it wants to access a particular segment, let's suppose the microprocessor wants to access the code segment, it will just access the code segment register, the CS register, which is of 16-bit. So a register is basically a device which is capable of storing some data in it, right? So the code segment will be able to store some instructions that resides in the code segment. Similarly, the stack segment, the data segment and ES, they are all the registers and not the segments. So next one is the IP. IP is the offset address of the code segment and it points to the next instruction that needs to be executed by the microprocessor. So now we have studied about these segment registers and now we have a basic understanding of the memory and how a processor will access a particular instruction inside the memory. So now the code segment register has the segment address of the particular segment and the offset register will point to a particular instruction. But the microprocessor, if it wants to access a particular instruction, it will calculate a physical address. So you can see here I have written a formula type here which calculates the physical address. So physical address is the actual address where the instruction is stored in the memory. So it is calculated by segment address into 10h plus the offset address. So if you have the offset address and the segment address, you can obviously calculate the physical address of any instruction. So you can see this circuit here. I've already told that it is used to do some calculations, and in the BIU, in the bus interface unit, it calculates the addresses, or I should say the physical addresses. So we have discussed about the physical address. So let me just give you an example of how to calculate a physical address. So in order to calculate a physical address, let's suppose we have a CS segment register has a data, let's say 1000H, and 1000H we have already discussed this hexadecimal format in the previous video. We know that this is a 16-bit instruction or the 16-bit. This is actually the 16-bit address. So you can see that it can be this is the segment register or the segment address. Now we have, let's suppose the instruction pointer is pointing to the address, let's say 2345H. So now we have the offset address and we have the segment address. So to calculate the physical address, what we will just do is we will just add a 0 we will append a 0 in front of the segment register, so it will become 1 0 0 0 and another 0, and then we will add the offset address, which is 2 3 4 5. So what is the physical address that we have obtained? It is 1 2 3 4 5 H. So this is the physical address of the instruction that we want to access, because the microprocessor it's just concerned with the instruction, right? So it needs to access the physical address of the instruction, which is calculated by this circuit, and then this is the data bus. So once you have calculated the address of a physical address, you have now obtained the instruction. Now you will pass it to this 6-byte prefetch queue or to the memory and IO or the input output devices. So once the instruction is obtained through the physical address, it just passes through the data bus, and then instead of passing this whole instruction directly to the execution unit, we do not pass it directly to the execution unit. We will store it in a prefetch queue. Now to understand what is prefetch queue, the 6-byte prefetch queue, if we want to understand this concept, we will first have to understand the queue. What exactly is a queue? So a queue follows a FIFO structure, FIFO manner, which means the first instruction first in first out. So the first instruction that will get inside the in this queue, it will get out first. It will get out of this queue first. So that's why we're using a queue. Why we are not using a stack? Because a stack follows a LIFO structure, and LIFO means last in first out. So this means the element that is inserted in the last is getting out, which we do not want. The ideal situation is to use a queue. Alright, so why we are using a queue? Because once you are fetching the instruction, it gets stored in the queue. And once it gets stored in the queue, the first instruction will get passed to the execution unit after it is passed to the control section. We will discuss about the control section also. So once the first instruction goes into the execution unit, at the same time it will fetch the next instruction and it will insert it inside this queue. So basically this prefetch queue supports parallelism or pipelining. So it's a 6-byte prefetch queue. So one important thing to note here at this point is that it's not necessarily that each and every instruction is of 1 byte. So I might have written it 1 2 3 4 5 6. It does not mean that an instruction needs to be of 1 byte. An instruction can be of 2 bytes. It can be more than 2 bytes, right? So we know that 2 byte means 16 bits, so obviously it cannot be more than 2 bytes. So this means that if there is an instruction which is fetched from the memory, now it is inside the queue. Now the queue will push the instruction which is first fetched. Now it will pass it to the control section, and there is also a condition which determines whether it should pass to the control section or directly to the execution unit. For that, we will have to understand. I will just give you an example of a instruction, and we will be able to understand what is the use of control section. Alright, so let's suppose we have an instruction. I will write here add BL, or let's just write here add BL comma CL. Now this is an instruction in the assembly programming. in the assembly language. So in assembly programming language, we have got a particular instruction, and we will study about more instructions in the assembly language in more detail. But in this video, I'm just going to give you a very simple assembly instruction, which is used to add the two registers and store the result into the first register. Alright, so this is the instruction add. Add is known as it's just the operation that it is going to perform, and each and every operation has some operation code, which we call it as the opcode. So every instruction has an opcode. So opcode basically specifies what operation that instruction is going to perform. And opcode, we will study opcode in detail. It's a sequence of bits which is fixed, so the microprocessor will be able to understand, the execution unit will be able to understand that the opcode, what exactly the opcode is. So remember that the microprocessor can only execute an instruction only if it is in a binary format. It cannot execute this assembly instruction which I've shown here. It cannot execute this instruction directly. So the this whole bus interface unit, when it passes the whole instruction, it will first have to decode it. So that the execution unit can easily perform the instruction given to it. Alright, so that's why I have written here opcode. So the opcode is obtained and it is passed to the control section, which will just decode this whole instruction, and then after decoding it will pass it to the whole execution unit. So this is an example of an add instruction. So let's suppose the BL is a register and it has some data, let's say 04H. So we know that this is a 8-bit data, and let's suppose the CL has data 03H. So this is also an 8-bit data. So BL is of 8-bit and CL is of 8-bit. And when you will add these two, what will you get? You will get 07H, and basically 07H is going to store in the BL. So when we say add BL comma CL, we perform the operation add on these two components, and in this manner I can also write it like this: BL plus CL. I can also write this instruction like this, but in the assembly format it is written like this, which means that you are going to add the two data inside these two registers and you're going to store it in the first register. So that's why this one is known as the source register and this one is known as the destination register, because we are going to store the destination, the result in the destination. Alright, so now we have studied about the BIU. So we have also studied that microprocessor does three things. The first is to fetch, the second is to decode, and the third is to execute. So now we have covered the fetch and the decode part. So I will just summarize it very quickly. The bus interface unit will have these registers and an instruction pointer which will point to the next instruction. The physical address is calculated by this structure, and then the required instruction is passed to the prefetch queue. And at the time it is passed, it will just pass the queue will pass the first instruction inserted, because it follows the FIFO format. It will pass it to the control section, which will just determine the opcode. Opcode is the operation code which specifies what is the operation that the instruction is going to perform, and it is basically in the assembly language. So once it is calculated, it will just pass the operand. Let me show you what is an operand. in this instruction, you can see here add BL CL. This is known as the operand. This one is the operand, and this whole is the opcode. Alright, so the control section will just decode the whole instruction, and then after decoding it, it will pass it to the execution unit. And we know that execution unit can perform the arithmetic or the actual execution only if it is in a binary format, because microprocessor can only understand the binary format. So in the execution unit, so you can see here we again have this structure, and this is known as ALU this time. ALU means arithmetic logic unit, and this is of 16-bit. This means that the structure can do operations or the arithmetic of up to 16-bit instructions. So you can see that in this we have shown an example where we have given this instruction to the execution unit. So we know that BL is 04H and CL is 03H. So now you can see I have just shown here that 04 the actual data and 03H is passed to the arithmetic logic unit, and this circuit will automatically see the opcode. Opcode is also some sequence of bits which determines which operation this arithmetic logic unit should perform, whether it should be addition or moving, or we will study more about this in detail in the further coming tutorials. So now after performing all the arithmetic, it will pass the result, which is this should be 07. So 07 is passed to this line, and once it is passed to this line, this is the result. Now just focus on this component, which is the operands and the flags, and both of these registers are basically 16-bit registers. The operand is basically the operands are basically known as the temporary registers. I'm going to write here temporary registers. And to explain the use of temporary registers, I will give you another example of an assembly language instruction. So the instruction is XCHG, also known as the exchange or the swap instruction, and let's say I say BX, CX. Now this instruction is used to swap the values of inside these two registers, which is the BX and the CX. At this point we're just calling them instructions. We will discuss this in detail when we will come to this whole structure. You can see BX, CX here. So these are basically just registers that contain some data. So we will this instruction will swap the data of these two registers. Now in order to do the swap work, we know that we will have to make use of a temporary register. So once we will first store the value of CX in the temporary register, and then we are going to make the swap. We know how to do the swapping. I know you know a little bit of coding. We have done swapping in C++ also, so that's the same scenario here. So we will use operands, and the second one is the flags. And basically flags, we will study different types of flags in the further coming tutorials, and it contains basically the status about the status of about the current result. So I'm going to write here about current result. For example, if the result is 0, or if the result is positive, negative, or if there is a carry or not. So similarly, there can be different types of flag registers which determine about the status of the current result. So the result that you have obtained from the ALU, if it is 0, if it is of positive sign, or if it is negative, if it is carry, for these different you can see status, we have different types of flags. We have the carry flag, we have the 0 flag, and similarly so on. We will study about all of them in detail in a separate video. Alright, so now you can see what we have done is we have now fetched the instruction from the main memory by calculating the physical address, inserted in the queue. The queue will decode, will pass the instruction to the control section where it is decoded. After passing the instruction, after decoding it, you will pass it to the execution unit, which will just perform the arithmetic operations, and it will make use of the flags and the operands. It will also pass the whole you can say the result to this line, which will be able to store some data in these registers. So now let's study about this component, which is the last component which we are going to study. So you can see that in this part, let me just use another color for that. So let's use this color, and in this part, which you can see, this part contains some registers in it. Now you can see that this whole structure is divided into two parts, and the reason is because that these two parts are of 8 bits each. So you can see that 8 bit and 8 bit. So AL is obviously a register, and all of these registers you can see AH, BH, CH, DH, similarly AL, BL, CL and DL. All of these registers are known as general purpose register. General purpose registers. And basically in the next video we're going to study the segment registers, what are their uses, and the uses of these general purpose registers also. Basically we know that registers will contain some data, and in this component the data is relevant to the execution unit. So you can see that we might need some data, we might need to store the result inside some registers. For that we cannot use the segment registers, so we have some general purpose registers or some multi-purpose registers, which we will discuss in the next video. So you can see that when we see AH, AL, when we combine both of them we get AX, which is of 16-bit. You can concentrate here, it is of AX is of 16-bit register. So this register is divided into two parts. AL means lower bit, H means the higher bit. So let me explain this last topic to you very quickly. So let's suppose you have data 1, 2, 3, 4, H. Now we know that this is a 16-bit data, and we have already seen the hexadecimal format. We can just make use of the hexadecimal table that we have drawn, and we can just decode it into the format. And it turns out that each and every you can see that if it is 1, it is of 4 bits, and similarly this is of 4 bits, this is of 4. So 4 times 4 means that this is a 16-bit data. So 16-bit data, you can directly store this data into an AX register. You can directly store this data, the whole data of 16-bit in the AX register, and the reason is because it is of 16 bits. But you cannot store the whole 16-bit data into the AL or AX, which you can see here, because AL and AH are of 8 bits. The reason why we have divided this whole data or AX into AH plus AL, the reason is because it is used to manage the lower and the higher bit. So you can see that this part and this part, when you divide this 16-bit instruction into two 8-bit, This is known as the lower bit and this one is known as the higher bit. So higher byte, because 4 plus 4 will give you 8 bit, so 8 bit is 1 byte. So this contains the higher byte and this one contains the lower byte. Alright, so if this is a 16-bit instruction, what we can alternatively do is, instead of storing the whole 16-bit instruction in the AX, we will store 12 in AH and 34 in AL, and when we will just, the combination will give us 1 2 3 4 H, and we will study about all of them in detail in the further coming tutorials. So in this whole video we have discussed about the working of the microprocessor, specifically 8086, which is a 16-bit microprocessor, and this whole knowledge of different components will help us in understanding further more concepts. We're going to understand some more concepts, and this knowledge will help us in understanding the concepts more easily, and we will be able to see how the microprocessor actually executes instruction. We will be studying the assembly programming language, some of the instructions in it, and we will see how the whole instruction is actually executed. So this is basically an architecture of 8086 microprocessor. This is the memory structure. We now know how to calculate the physical address. And now in the next video, we are going to talk about the general purpose registers, and then we will talk about the segment registers. One last thing to note here is that all of these registers, which are of 16 bits, these are known as the offset registers. And remember that these registers, you can see that these are the offset registers, and you can locate it here in this diagram. So you can see that for each and every segment we have a dedicated offset address with a dedicated name. So stack address, the stack segment can have two offset registers. One is the BP and the SP. The data segment have the SI and extra has the DI. And you can see that since it is 16-bit, it is from FFFH to 000H. Alright, so in the next tutorial we will be studying about the general purpose registers. So thanks for watching.